All right. This thing on? Everyone can hear me? Great. Perfect. Thank you all for joining me here in what I think is a 60-minute talk. Is it 50? 60? Perfect. I think I can make that work. We'll see. So they asked me to stay within these bounds a little, so I'll mostly be presenting to you. I'm sorry to the people on the right, but it is what it is. At least you have a screen. Welcome, everyone, to this talk about optimizing your HTTP client usage. And today we're going to talk about HTTP client, which obviously you all know what it is, so we're not going to discuss that. What are we going to discuss is how to correctly use it. Because in my years as a developer, as a tech lead, as an architect, I've seen a lot of misuse of this tiny little utility class in .NET. Okay, for starters, who here does a REST call on a regular basis? Great, you're in the right talk. My name is Nico. I come from Belgium, the country where they cancel your flight last minute because of an unannounced strike, but I made it, so here we are. I work as a cloud solution architect at Microsoft Belgium, where I help customers move their applications into the cloud, put some agentic workflows in there, and so on and so on. I also do a lot of community stuff back home. I run a user group called the Visual Studio User Group. I'm part of the crew of a local conference called Techorama. I've written a couple of books. They don't matter. Don't bother. Go look them up. They're old. But if you want to get in touch with me, you can find me on Blue Sky or on LinkedIn. That's the two social platforms where I'm active, where you can find me. If you have any questions after this talk, you can find me here, or you can reach out online through those channels. All right. Why would you care about HTTP client and by using it correctly? That's simple. As we've seen, everyone here does REST calls. Everyone uses HTTP client. But, as mentioned in the intro, there are a lot of ways of using it wrong. And if you use your HTTP client wrong, and this is as easy as instantiating it in the wrong place, you can create socket exhaustions. You can create stale DNS records. You can do a lot of stuff wrong. And because HTTP client is so important, it powers everything in .NET, all our REST calls. Everything, well, almost everything, is client-server based these days through REST. So we better know how to use this correctly. Now, even in these days of agentic development with your Claude and your Copilots and you name it, it's important to know this. Because the code that these agents generate, those are trained on what it can find online, and there's a lot of wrong stuff online. Luckily, also a lot of correct stuff. So if your agents are creating HTTP client code, REST code, do code review those. And do make sure that the guidelines that I will give you today, that those are in place as well. What is HTTP client, really? Have you ever gone and checked the code behind HTTP client? Who has ever checked it? A couple of people? All right. I've done it, so you don't have to. You're welcome. So HTTP client lives in system.net.http in that namespace. It's out on GitHub. I've put the source or the link to the source right there. It's a very simple class. There's nothing special in there. It's basically just a collection of different settings. And those settings are used to send requests and receive responses from a REST endpoint. That's what it does. Every HTTP client instance has an isolated connection pool, meaning if you create 3, 4, 5 instances, those all have their own connection pools. And that should be a trigger right there on how to correctly use that. And we'll get into that in just a second. Now, if you look at the kind of hierarchy of HTTP client implements HTTP message invoker, which implements IDisposable. And this is the first pitfall for a lot of people. IDisposable means put it in a using block, right? Don't ever do that with HTTP client. Because if you do that, your connection gets disposed. The next request you make, you have to create a new connection. And I will get to that in the next slide. But first, there's a sockets HTTP handler there underlying. That's where the real magic sits. That's the part, that's the class that creates the actual connection to your endpoint, that sends your request and receives your responses. That's sockets HTTP handler. Now, currently, we only have the one HTTP client. If you go back a couple of years, there are 3 versions. You had the .NET Core version, back when it was still called .NET Core in 2.1. You had the WinRT version for when we were building the Metro apps on Windows 8. Remember that? That was fun. And I don't mean that sarcastically. I actually like doing that. And then there was another version in the Mono runtime for your Xamarin apps, back when Xamarin wasn't owned by Microsoft yet. So 3 different versions. Not only were there different versions, they also had a different base class. So the underlying implementation was different and the API surface was different. So if you thought you knew HttpClient from your Xamarin days and you came to .NET Core, it was different. Luckily, all of that got consolidated, and now there's just the one HttpClient that rules them all. Now, how does this work? When you call client.getAsync and you pass in a URI, because this is as easy as it gets. It's a very easy class to use. But what happens under the hood? First of all, HTTP calls are TCP-based, meaning you have to create a TCP connection. Before you can create a TCP connection, you have to know where your endpoint lives. So first thing that happens is the endpoint gets resolved into an IP address through a DNS call. That gets cached into your HTTP client instance. From there, we're good to go. We know what the IP address is. And the TCP handshake starts. What does that handshake look like? First of all, your client sends a synchronization sequence number to the server. And that SYN number, that is basically the first part of the data. The data that will flow from client to server will start with this. Server says, that looks good, I acknowledge. Client returns, I acknowledge that you acknowledge. Luckily, that's where it ends. And you have your TCP connection made. That happens every time you create a new connection. Now, we have our TCP connection, but we want to do things secure, so we're using HTTPS. Meaning, next thing we need is our SSL handshake. That starts with a TLS from the client to the server call that says, hello, I want to communicate with you in a secure manner. Server replies with, OK, sure, why not? This is the TLS version I can support you with. Here's a certificate. I'm done with saying hello. Client sends back, here's a cipher that I want to use. Here's the key exchange. And the server returns, OK, we're good to go. And we're connected. TLS handshake completed. Those 3 things, resolving the IP address, doing the TCP handshake, doing the TLS handshake, all of those things happen every time you create a new connection. Remember, 2 slides ago, I told you that every HTTP client has its own isolated connection pool. Meaning, if you put your HTTP client in a using block because you're a good developer and you see iDisposable, so let's put it in there. Every time you do that call, all of this happens. If you reuse your existing HTTP client, then this only happens once, unless it times out. So that's already a big difference. Now, what's in a request? A request is an envelope and contains a bunch of things. The method that we're doing, get, post, put, patch, delete, and so on. What protocol version we're using, HTTP 1.1, for example, and what the endpoint is. And there's an example right there with the get products 1, 2, 3. There's a bunch of headers in there that's saying which hosts is it coming from, what is the user agent, what encoding are we accepting, and then a bunch of user-defined headers we can put in there. For example, authorization headers, and so on. There's the content. That can be content. There doesn't have to be content. Which is the serialized payload. And then there's the encoding, HTTP 1.1, 2, 3, and so on. And all of that gets sent over the TCP channel. and then the response comes back. Let's see how this works, and let's see some first pitfalls. I have an API running in the back here that returns very exciting, totally randomly generated weather information. So there are two endpoints. There's the weather forecast, and if I refresh, you'll see it load for a bit, because there's an artificial delay of 2 seconds there, just to prove a point. So it will wait for 2 seconds and then return some data. And then there's the weather forecasts, which returns an array without a delay of multiple forecasts. That's the API that's running in the back. What that looks like, that doesn't matter at all. We're interested in the client side today. So switching to Visual Studio, is this font size big enough? People in the back, want it bigger? Bigger? That's why I left this open. Let's see what 20 does. How's that? Perfect? Nice. Okay, let's run this first. Zoom in a little bit. And you'll see a bunch of calls starting to happen. And this is just a parallel version of calling that weather forecasts endpoint 20,000 times. At one point, this should start to fail, unless it doesn't. There we go. There we go. We get a socket exception. We ran out of connections. That's what happens. And it actually took a long time. Usually it goes a lot faster. The reason for that is, if you look at the code, this is a list of tasks, 20,000 of them. And in those 20,000 tasks, each one creates a new HTTP client and disposes it using the iDisposable pattern. Exactly what I just told you not to do, and now you see why. Things will break. Now, if I just take this and put it outside of my loop, then I'm reusing that instance across all 20,000 calls. I'm not going to let it run anymore. Just know that this time it will finish. I will give you a QR code at the end to the code. Then you can try this out yourself. So again, reusing your client instead of creating new instances every single time. Right, so one way to do it is to just new up a new HTTP client, which you can do, and then make it long-lived. Another way to do it, or a more common way to do it, is by using dependency injection. I'm just going to comment out this code like that. Go to this. Very similar, just not the parallel thing. We just do one call by newing up an HTTP client. If you want to do this, it's an industry standard to use in version of control, so we use the built-in dependency injection. This is a console application. You can use Microsoft's dependency injection container here as well. That's what I want to show you here. The only thing you need to do is add 2 NuGet packages. Zoom in again. So we have Microsoft.extensions.dependency injection. This enables the service collection that you know from ASP.NET, pulls that into a console application. And then there's Microsoft.extensions.htp. And this will give you a couple of overloads so that you can easily inject HTTP clients and HttpClientFactory in your dependency container. Install that as well. There we go. OK. Let's remove this client here, and we'll start building our services. We start by newing up a new service collection. That's not a new service collection. This is. And then using that Microsoft.extensions.htp library, we can now say add HTTP client. Then we build that into a provider, build service provider. And then we can use that provider to get a required service of IHttpClientFactory. So this is not a client yet, but this is the factory. Where's my mouse? There. Factory. Oops, that was the wrong button, sorry. From that factory, and I will go into HttpClientFactory in just a second, we can create a client. And we're good to go. So we're using dependency injection here in the console application. Just wanted to show you that you can do that. You don't need to be in ASP.NET context. We are registering our HttpClientFactory within our service collection. We're pulling that out as required service. Obviously, you would inject this as a constructor or as a property injection. Here, we're just pulling it out directly. And with that factory, you can create a new client. And then we use that client to get string async. If you run this, very exciting, then you get some weather forecast right here at the top. Great. Now, let me switch back to the slides real quick and talk about Client Factory. The IHttpClientFactory is an interface, obviously. And this is an interface that, well, creates HTTP clients. It's a factory to create clients. It's what the name says. Now, contrary to having long-lived HTTP client instances, the ones that are created by your client factory, those are short-lived. You create it, you let it do its thing, and it gets disposed, and it's done. But you just told us to use long-lived because of all the connection things. Yes, but HttpClientFactory has a reusable pool of connections. It caches the connections for you and injects that in those short-lived instances. Meaning that you have the advantage of a long-lived HTTP client and the advantage of using short-lived objects. You don't keep them around in memory, you have your factory. Now, why would you use this? Because you can configure your HttpClientFactory to have typed clients and named clients. You can create different configurations. Imagine you are building a client application that connects to 5 APIs, 5 totally different APIs. Some of them you own and you build, others are third-party. They each have their own separate configuration to connect to. For starters, they have a different base address. Some might require authentication, some might be public. Some might require specific headers to be sent along, and so on. With HttpClientFactory, you can define all those, either as named clients or as typed clients. And I have demos of that. I will show you how that works. But then you can just inject a client, an HTTP client, wherever needed, the correct one, and just go to wherever without having to duplicate that configuration all over the place. That's what makes this very interesting. Now, do be careful, because this is a reusable message handler pool that's in there. Do be careful with cookies. If you put sensitive information in cookies, that cookie container is also shared across those HTTP client instances. So do be careful with that. Now, if you decide I do not want to use Client Factory, I want to use HTTP clients, then reuse instead of renew, as we've discussed. Don't dispose them, but maybe consider setting the connection lifetime. What is the connection lifetime? As the name implies, it's how long your connection stays open before it times out and has to reconnect. Why would you do that? Because you have a risk of having DNS staleness. If the IP address behind the host name of your base address changes, then the DNS gets updated, but you're not pulling the DNS anymore, because that only happens before your initial connection, before the initial TCP handshake. So staleness might happen. If you're in an environment where you don't control when the IP address changes, you might consider setting this to 15, 20, 30 minutes. Worst case scenario, there are a couple of users that are seeing timeouts or 404s for 15 minutes before the DNS updates. But it will recover by itself. So keep that in mind. If you are using your HttpClientFactory, that has a default instance for your connection or a default timeout. I think 2 or 5 minutes. I don't know by heart. I would need to check. But that does it by default. So again, an upside of using that client factory. All right, let's take a look at how that works. Going back to Visual Studio. Closing all these things and using that. Okay. I have a Blazor application here. It's using the same weather API. And all it does is when you open the weather page, it uses the array call now. So whenever I refresh, I get new information. Nothing exciting. It just works. All right. Let's have a look at some code. So in program.cs, there's nothing there yet. We're not doing it the way we should be doing it. And if we look at the weather page, so the weather page is using a new HTTP client every time you load the page. And it's disposing that instance when the page closes. So not the correct way to go. Let's refactor. For starters, we will go back to program.cs and we will add our HTTP client so that we can use our HttpClientFactory. Then, right here, we can go. We don't need client. We need our client factory. We'll call that factory. Should not be read-only. And we'll inject this. You don't want to inject? Is it capital? There we go. Okay, let's make it public just to be sure. And then in here we can create a client out of that. Factory.create client. And then use that. All right, we are now using a reusable factory. Just going to do a quick check to see if everything is working. And everything is still working. Except now we are reusing our HTTP client instance, or our HTTP client factory. We are still creating a new short-lived instance every time, but that's exactly what we want. Now, this is all running on localhost, right? Both client, server, localhost, everything is fine. As long as my PC is up and running, we're all dandy. This is not always the case, of course. When you are running in production, you have different servers. You might not even control your backend. That might be third party. So this call, this getString async, this might fail, but we're not catching anything. We're not handling failed requests. To do that, we are going to change from getString async to catching an HTTP response message. So this will be the response. We are using our client and we are calling getAsync. And then I'll just do this and paste that there. Take this one out. And maybe give us some room so that we can see what we're doing. All right. We're calling getAsync. So what's the difference? If you call getString async, then you are basically telling your HTTP client, I am expecting a string object. Might be JSON, might be something else, might be XML, but something string-based. That's what I'm expecting. The system will still receive an HTTP response message, will convert that into a string and return that. So this can fail at many places. This can fail at the request. This can fail because there is no string in the body that it returns. This can fail for many other reasons. So not really a solid base to work with. With getAsync, you always get a response message, unless there's no connection. But let's just for now assume that the connection is OK. With getAsync, you always get a response. Even if it's an HTTP 500, you still get a response message. You just need to inspect what HTTP code is in there. And something we can do here is, let me zoom in again. There is a status code. And this is actually your HTTP response code. Hopefully it'll be 200, but this might be 400 or in the 400 range, 500, and so on. There is also a reason if there is a success status code. There is also a Boolean that says, is success status code. This basically returns true if the status code is in the 200 range. That's what it does. Just an easy shorthand, just like ensure success status code. This is a method on your response message that says, this will throw an exception if the isSuccess status code is false. This is easy code, right? I could have written this myself. This is 2 lines, but it is an easy to use shorthand. So we are going to use it. Ensure success status code. This will crash if something goes wrong, which means we need to put a try-catch around that. What was the type of exception? HTTP request exception. Do something here. That's great. And then put this into the try. Let's put that in there as well. There we go. OK. Pro tip, a little outside of the scope of this session. If you are doing try-catch statements, only do them whenever you're not in control. Right? Unless you're doing business exceptions for validation purposes and so on, then that's fine. If you are doing other catches, don't do it everywhere. Only use it when connecting to external systems, when you're doing disk I/O, for example, or network I/O. You don't have control over those things. Otherwise, make sure things can't go wrong. Because try-catch it has an impact on your performance, right? Also, don't just do catch exception. I've seen this way too much. Exception is the base class of all exceptions, so this will just swallow everything. If that's what you're looking for, fine. If it's not what you're looking for explicitly, then catch your explicit exceptions. Only catch what you can't control, right? I have seen people putting try-catch around everything. And I do mean literally everything. In WinForms back in the days, you could show a pop-up, like some window.show. I've seen people put try-catch around that. That's a system, that's a call into .NET directly, a one-line call, try-catch. So be careful with that. OK, we have that. OK, so we have our response message, we have our success status code. Moving on, we need some results. We are actually almost ready to return. In our response object, there is a content. That content, we can read as several things. We can read this as a byte array for images, for example. We can read it as a stream. We can read it as a string. But there's also a nice shorthand again that says, read it as a JSON. And this here lies into this type of object. This is using system.text.json under the hood. In the overloads, there's an overload somewhere where you can pass in your JSON options as well, if you want to control that a bit. If the read from JSON is not sufficient for you because of your specific JSON setup, then just read a string and use your own JSON deserializer to go to a JSON object or to a .NET object from there. For now, this is fine. we want weather forecast array. This is giving me squigglies because it's async, and I need to await this. Or at least that's what I thought. Oh no. I don't have to return just yet. It's like this. All right, let's try it out. So what have we done so far? My function lock is off. That clarifies some things. What have we done so far? We've gone from getAstring async to getAsync. We have made sure that we are not getting any error codes from our server. And we have catched possible exceptions that are thrown, and we have used our content from that response message to deserialize in an easy way to our .NET objects. And most importantly, we've gone from short-lived HTTP client instances to short-lived HTTP client instances, but controlled by an HTTP client factory. Okay, now, what good is a factory if it doesn't do anything for us? Let's take out this base address. Move into our program, add HTTP client, and then we can do something like this. Base address, is that a URI? That's a URI. Like that, wrong overload probably. So we'll name it. Let's do it like this. This is now a named HTTP client. We have given this specific configuration of our API a name. It's called Weather API. It has defined the base address. That's what we have. If we now go back to our page right here, and we create a client. Where do I create my client? Here. One of the overloads expects a name. Put in the same name here, weather API. We'll put a breakpoint there, see what happens. You probably can already guess. We have a client, and if we go look at the base address, that's the one we defined in program.cs. So that configuration that we do in one specific place in our application, our application startup and application bootstrapping, that gets injected now wherever we need it. Right? And this makes it very easy, for example, to move from environment to environment. If you want to go from dev to test to act to prod, you don't have to configure your app settings all across your application. You just do it in your program.cs. And you could put, we can put all the configuration in there, whatever you need. So that's the named instances, and those work. Those are nice to work with. Another one are the typed clients. And that looks like this. If you want to make a typed instance of HTTP client, you create a new class, and you make sure that the parameter that you're expecting in your constructor is an HTTP client. That's all you need to do. In this class, I am getting the weather async. Yes, I know I'm doing it in the old way that we don't supposed to use anymore, but for the sake of the demo, that's fine, just to keep the code a bit short. Going back to the weather client, we no longer need our client factory. Now we need a weather client, which is a class. I will name that client, get set. And once again, we are injecting this. We don't need this. And we can just say forecasts equals await client.getWeatherAsync. All of these codes can just go. And that's what I like a lot about typed clients. It keeps your actual pages very small. I'm just doing one method call, and everything behind it, all the logic of doing retries and so on, that's all abstracted away in that class by itself. That's why I personally prefer typed clients over named clients, but it's just a matter of personal flavor, right? There's nothing wrong with using named clients. Moving back here, I can remove the name. And HttpClient has a generic overload where you just specify the type. And then the configuration stays the same. With the generic overload, you don't have to specify a name parameter, which makes sense because you're not using named anymore. And is the breakpoint still there? No, it's gone. Let's try this again. Go to the weather page. Oh, it's already there. Looking at that client, there's an HTTP client in there. Also has that same base address. If I press F5, then everything continues. I did remove the breakpoint, didn't I? No. Anyway, that now works with a typed client. Right? Cool stuff. Okay, moving on to some more advanced topics. We've now seen the correct use of HTTP clients. Wherever you can, please use your HttpClientFactory. Decide on named clients, typed clients, doesn't matter. And if you want to really extend the way you use your HTTP clients, you can implement delegating handlers. Handlers are some sort of middleware. They sit between your request and your response. Your requests get intercepted. You can manipulate the request, let it go through. The response gets intercepted. You can manipulate that, let it go through. And these things, you can chain those. And very, very important here is the order in which you register them, because that's the order that they will trigger. As you see here on the schema, you have your HTTP client. On the left side, you have your request. That goes through message handler 1, handler 2, and then finally the HTTP client handler, which is the built-in one. The HTTP client is a built-in HTTP client handler, and that one actually triggers your request. That does the heavy lifting. And that one always comes at the end. So everything goes through. The request reaches the endpoint, the response comes back, and it goes through all of them again in reverse order. Basically what happens is all those handlers have a method that gets called, and there's an await in there that you call yourself to let the request move on, and it awaits until the response comes back. So you can manipulate both request and response in one handler. Why would you use this? For example, if you want to fetch an access token, bearer tokens, you could do that in handler. Just Eat has a lot of open source stuff, and you check out that link right there. They have an interceptor where they intercept all the requests when they are running in a test suite. They intercept all the requests and replace it with stubs. Instead of having to mock their HTTP clients, they just do it this way. They intercept everything and just send dummy responses back. Now, there are a couple of limits here. You can't do asynchronous delegating handlers. You can't do that. This is a very much synchronous story because you're moving from one to the next and back again. You also can't change your settings on your HTTP client because you are in the middle of a request-response flow. So your client settings don't matter anymore because they've all been set and used in this request already. Same with the sockets HTTP handler config, which is more deep down in your HTTP client. You can't change those anymore either. Oh, that's the next thing. You know what? Let's go through the slides first. Resiliency is also something that's very important because your request can fail. What do you do? Let's say your network just I mean, Wi-Fi is not the most stable thing in the world. It could just drop at the moment you do your request. What happens then? You just let it fail, or you're gonna retry. That's where your resiliency comes in. You get to retry stuff. And same for, well, this will time out, but what with throttling, an API that gets hit really hard. Imagine the most popular festival in Denmark opens the gates to ticket sales. That will hit the API hard. You need a way around that. Connections that drop. And the most dangerous thing here is if that server that hosts the API goes down for 5 minutes. And you have 2 million people just hammering on. As soon as it comes back up, you get 2 million requests in a couple of milliseconds. If your server can't take that load, it'll just go down again. That's called the thundering herd. And if you do very naive retry implementations in your code, then your code will do this for you. It will just keep retrying, and then it sees, oh, the gates are open again, let's go. And the system will go down. Now, there are libraries like Poly that handle this. What you do with Poly is if you implement their retry mechanism, you specify how many times you want to retry. A good default there is 5. But every time between those retries, you let a bit longer in between. First, 2 seconds, 4 seconds, 6 seconds, so on, whatever. You can specify that. The thing is, there's a lot of default implementations of this. If you look at the Poly documentation, if you look at their samples, there are defaults in there, and we are all lazy, so we just copy the defaults, right? That's what we do, easy. Now, that does not stop the thundering herd. If everyone does it, you will have the same thing again. And that's why Poly introduces some jitter. If you say retry after 2 seconds and you have enabled the jitter function, then at one point it might be 2 seconds, but it might also be 2.2, 1.9, 2.3, and so on. So a little bit of jitter. And that might be just enough to let the server catch his breath and come back online. Other interesting things there is the circuit breaker pattern. Circuit breaker, you have your request that goes through, everything works, and then imagine that the request fails again. You can keep retrying, but at one point, the circuit will open. Imagine this as a circuit breaker that you have in your home. When it opens, the power can no longer flow, requests no longer flow, and Poly will no longer allow you to send the request. It will block it because it's open, right? And then it has a default time. After that time, it will try to reach the endpoint again. If it can find it, it will half close the circuit and allow the next call to go through. If the next call goes through, the circuit will close completely and you're good to go again. If it doesn't go through, it trips again. That's a circuit breaker pattern. It kind of avoids you doing too many network calls to an endpoint that's no longer there. That helps both you as a client developer, helps both the server people to let the server come back on. All right, let's have a look at those. Because we've seen a couple of topics, we'll go over them one by one. Close all the tabs. We're staying with the Blazor sample for now. We have a logging handler. So I have 2 handlers here. And a handler inherits from Delegating handler, which is the base class. And then you can override the send async method. And that's all you need to do. Just override that. These are very simple. So this is a logging handler. You can intercept your request, your response, do some logging, whatever you want. So I'm just writing to my console, logging request to this URI. And this is actually where it will wait. You call your base class, you await the send async method of the base class, and it will continue down the flow of all the handlers. And when the final handler is reached and the response is coming back, then those awaits will call the continuation. And you will move back up the line. That's how it works. There's another handler here, authentication handler, does the exact same thing. Except here we are adding a handler or a header for the authorization. It's just a dummy value, nothing special. But this would be a good place to get your token from your OIDP server and send everything. Now, how do you use this? Going back here to our add HTTP client, there is, I have to check what it was called. Add HTTP message handler, that's the one. We are doing logging handler. And let's put the second one in there as well. That's how easy it is to configure this chain of handlers. And again, the order matters because requests will go logging auth, and then coming back with response will go auth logging. And switching back to the handlers real quick. Normally, you wouldn't do anything anymore here unless you want to do some extra logging or inspect the headers of the response or something. But you don't have to. You don't have to do anything here. You just return the response to let the flow continue. Okay. Let's see what happens. Go to the weather page. Oh, something went wrong. Ah, right. Every single time. So these handlers, they rely on your dependency injection. And of course, they won't be able to pull them in if I don't register them first. I swear I've done this talk 5 times now, and every single time I forget this. Builder.services. Was it add or was it register? Wow. Sorry? Add? Add singleton. Let's do scoped. Thank you. Add logging handler. Add auth handler. There we go. Let's run this. Should work now. For some reason, it still thinks there's a breakpoint there. Whatever. Okay. Going to the console. This is the logging that happened through my handlers. So you see the logging is coming first, the logging handler, then the authentication handler, then it received the authenticated response. So we're going back in reverse order, and we say HTTP OK. So that's my handlers working. Great. There's that. About 12 minutes left. That should be quite okay. Set this as a starter project. What do we have here? So this is next demo is Poly, the Poly library. Poly has become quite a default. It's an open source library. It's on GitHub. It's all about resiliency. It has become the default so much that Microsoft actually pulls it into their templates for ASP.NET. So you can use it there. In order to use it, we add a NuGet package to add the extension methods. And this is Microsoft.extensions.http.poly. There we go. Right. Next, you define a policy. And that's not the one yet. So we create a retry policy. And this comes from the HTTP policy extensions. Handle transient HTTP error. Retry async 3 times. That's my policy. This is actually configuring poly to retry on failure 3 times. Then we are adding our message handler. Underneath that, we can add a policy handler and add our retry policy. So all of this is also based on those delegating handlers, right? Because that's where you need to be. Let's run this. So this demo has a couple of things. There are some flaky endpoints in my API as well that will fail always, that will fail sometimes, and so on. So if we do eventual success, then it succeeds from the first time. Let's see what this does. OK, it keeps succeeding. But this is also my retry that's in there. Right? It retries 3 times. Within those 3 times, it always succeeds. Now, what I just mentioned is these 3 times, they will happen immediately. Fail, retry, fail, retry. You want to have some delay in there. So instead of retry async, we go for wait and retry async. So we're going to retry 3 times. We're pulling in our retry attempt. And this is where we can configure the amount of time that we wait between those retries. So we take time span from seconds. And then we use some math. And we just take 2 to the power of whatever attempt we're on. So every time it takes a bit longer. This is what I mentioned of being the default that Poly introduces in their samples and so on. So that's where that comes from. I'm not going to run it anymore. You get the gist. You know what will happen. Going to the circuit breaker. This is also a policy, right? So we have, again, the HTTP policy extensions, just like we did just now. Handle transient HTTP error, and then have our circuit breaker. And I've put this into an extension method just to prevent my program class of getting too big. So do some housekeeping there. Keep those together, your policies. Now, this is the configuration for it. We are allowing 3 events, 3 failure events in a row before we trip our circuit breaker. The duration will be 5 seconds, or 5 seconds. And then we put some console outputs. And you have events firing on break, on resets, and on half open, which matches with what I've shown you. When it breaks, then it will stay open for your 5 seconds, and nothing will go through anymore. When it resets, it closes again, and your data just flows again. On half open, it's kind of pinging, seeing if it can get through or not. And then we can just do what was it extending again? Policy builder. So here, instead of wait and retry async, we are doing get circuit breaker policy. With then the retry policy there, so now we have implemented our circuit breaker. We should be good to go. Again, for sake of time, not showing it anymore, but I do have a QR code within 2 slides, I think. that will give you the demo, and you can try it out for yourself. Play around with it. Clone it, maybe update some NuGet packages, and play around with it. See what you can do with the different settings. These are a couple of links that I've used to throw all of this together. They will take you down the rabbit hole of what TCP connections are, TLS connections, how networking works in .NET, and so on. It really is a rabbit hole, but it's very interesting stuff. This is where all the demos are. That's the link. The QR code takes you to that link. I'll leave this up for a while. Till I see all the phones go down. All right, everyone has it. Then I would like to say thank you. If you have any questions, feel free to come up to me, and I'll be happy to try and give you an answer. Thank you so much.